if you're on Discord or wherever and people are asking you about the exam date, it's much better if you don't actually write the date down. There's a couple of reasons for that. One is if you make a mistake, then that mistake is up there and people are writing it down and taking note of it, and they're getting it wrong. And the other thing is that it does occasionally change, so it's much better if you post the link. So here we can see this is. And so this is us here. So August 19th from 2 p.m. to August 23rd at 2 p.m. But that's by following, let's see if I can, that's by following this link up here. Hopefully it's showing you that. The link is posted in Discord, but you can just Google Carleton exam schedule and it'll come up. So there's that. Any questions about the exam or the format of it? So it is, you know, you have a range of time where you can start it, and it's 2 hours and it's 35 multiple choice. And we're going to go over, so some of those multiple choice are similar to what's in the practice exam. The practice exam is much more open-ended because you're trying to make you think about these things and understand them at a level that's deep enough that you can answer a bunch of different types of questions about those topics. Yeah, no solutions. I will go over tonight, I'll go over some strategies that you can use. We might do, I think, you know, I do a little bit of one or a little bit of another, and I'll answer any questions you have, but in general, there's going to be no solutions. You should just know how to do these questions. That's the accountability and algorithms beyond the exam. Maybe. So focus, primarily what's on the exam is the practice exam. So nobody's trying to fool you here. And yeah, so the exam was made last semester when we didn't reach accountability and algorithms. So no, you should expect 10 node graphs, yes. So they are made that way because it is open book. So the questions are a little bit more difficult. We'll get into that. So first of all, before we do get into that, so the idea, what I was going to do is I was going to do a review of everything in the class, and then I was going to take up the practice exam. But out of respect for your Friday night, I can reverse the order of that, so I can do the practice exam first, and then go over the general review of all the material. And if everybody happens to leave, that's fine. I'll finish the lecture and then I'll post it up after, and you can watch it or not as you want. But so just let me know if you'd prefer to do the practice exam first, or if you prefer to do the general review and then the practice exam. Since you guys showed up, I'll let you guys decide. General review first, sure. One for general review. Is that? Yeah, I think that's. I mean, it works better that way. You have some general questions about the practice that'll influence that decision. Yeah, okay, we'll do the general review first. I'll try not to take up too much of your time tonight. So it's just, you know, if it goes long, we'll take a break. If not, we'll finish when we finish. There is quite a bit of material, but it should go quickly because it is review. Any other questions? It's open book exam. I mean, if it was closed book, people would just make it open book anyway. I mean, there's nobody, you know. So it's open book, and that is why the questions are sort of a little bit more, I don't want to say difficult, but the complexity is higher. So it should take you longer to do them, and that's on purpose so that you don't have, you know, ideally, a good open book exam means you don't have enough time to actually look at the open book. So that's sort of the goal. So that means you have to study anyway. Sums and sets, yeah, for sure. We can, well, we'll take a look at everything. And there's a couple things I want to point out as well. I've been getting questions about, so sums and sets, I'll write that down. I've been getting questions about big O as well. So I'm going to skip a lot of details on the review, but if at any point you want to see some more detail, just stop me or, pipe up in the chat and let me know. All right. Any other questions? So the other thing, the format of this is a little bit different. So these are all my handwritten notes, and I wrote them tonight. I was gonna give the lecture in Linux. I want to migrate over because Windows has been a bit buggy on me. But when I did a sound check, I sounded like I was talking in a tin can. So I had to take all my notes from Linux and port them over. So it's anyway, you'll see. I had to export them as PDFs and then import them into OneNote. So it's just a little bit different, that's all. All right. Good, so should be looking at OneNote right now. I'll try and remember to screen share properly at the proper times. So this is, yeah, we're here tonight and we're done everything, all your marking, you should have all your marks back at this point, and disputing either assignment 4 or quiz 4. I forget when the deadlines are, but all right. So that's actually pretty short tonight. Where are we? All right. So here, yeah, these are my handwritten notes from some writing software in Linux. That's not, and if anybody actually knows about how to optimize a microphone in Linux, I would love to hear it. But yeah. Okay, so first we'll go over all the topics, and then we'll go into a little bit more detail in each of them. So yeah, we started with propositional logic. So that's, not P or Q, that sort of thing. Translations from logic to English and vice versa. And then we did predicate logic. So that's, for all and there exists. Inference and argument. So we learned how to make an argument by using inferences on, so we take things we know to be true and then we apply operations and come to other conclusions. Formal proof techniques. So direct proof is, well, if I want to prove that P implies Q, then I assume P is true, and I try to show that Q follows from that. Indirect proof, contradiction, case analysis. We'll go into those in more detail. Those are the main ones. Sequences and sums, set theory, graph theory, and then asymptotic analysis. So we learned how to analyze an algorithm and then count the operations and then put that into big O notation. And then we learned about functions, so injective, surjective, and bijective functions. And then we jumped into relations. So relations are a subset of the Cartesian product, and they're sort of similar to functions. And then we learned about countability, which won't be on the final, but you know what? Maybe I'll let me take that back. I'll double check if it's on the final. And my Wi-Fi seems a little low here, so I hope I'm not dropping anything. So yeah, let's assume countability is on there. Algorithms is not though. That's it. Okay. All right. So to start with, propositional logic. So a proposition is a declaration with a value of true or false. So it is raining. That can be true or false, and it's false in this case, at least here. Pi is greater than 3. Well, that's true, etc. So these are just statements we can assign a true or false value to. Atomic propositions mean they cannot be broken down further, which is, well, these are atomic propositions up here. They just mean that there's no logical operators with them. So the types of logical operators we looked at is the negation. So that's, sorry, that's this guy. So if something is true and I apply a negation, it becomes false. And if something is false and I apply a negation, it becomes true. And then we have the exclusive OR operator, the AND, the OR, and the implication. If you guys want, we can go over the truth tables of those things, unless you feel comfortable. I think AND and OR should be pretty straightforward. Exclusive OR and implies maybe a little less. Does anybody need to go over any of the truth tables for those? All right. Well, if you do, just speak up. So there are English equivalents to these operators. So I am wearing sandals and I am wearing socks. That's not true, I'm barefoot, but whatever. So that's, you know, this corresponds to the logical AND operator. And then I am a math instructor, or I like math, and maybe both. So that corresponds to the logical OR operator, which is that. And, you know, it has that in English, OR means both logical OR and exclusive OR. So you have to be aware of the context. So if I wrote something like, I can turn left or right, I can only turn one of those if I'm at an intersection. So this is the exclusive OR operator. Right, and then I am not tired, but I'm going to bed. So not tired, that's the negation operator. So, but here, that doubles as AND, right? So if we see a but, that's actually a logical AND operator. In English, it means something a little different, but yeah, in logic, it means the exact same. All right, so we can define logic expressions using truth tables. So if I have my P and Q here, then, you know, and typically we would, on the exam, we'll give you the order if we ask you any truth table questions, but typically we write them as true, 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 false, false, true, false, false. It sort of follows binary operators, counting by binary, but you know, just we will give you these if we need you to construct a truth table, and then you just give us, for instance, you would give us the final column. So yeah, just to be aware of that. And so two logical expressions are equivalent if the final column of the truth table is the same. Right, so no matter what I had up here, if I had something, I don't know what's equivalent to P and Q, I guess not P or not Q knotted, right? So that's logically equivalent, so it would have the same final column of the truth table. Right, so that means these two things are equivalent, this guy and this guy. All right, so a truth table has 2 to the power n rows, where n is the number of propositions, right? So the propositions in this case are P and Q, so this has 2 to the 2 rows, and we can see right here that it has 4 rows. The number of columns depends on the number of operators, right? So if you're asked a question like that, don't skip any columns. So every negation gets its own column, et cetera, et cetera. And these we've gone over on the assignments, or you guys had to do them on the assignments. So hopefully, you know, just don't skip any steps, and you'll get the number of columns. All right, so we can also two logically equivalent expressions can also be transformed into one another, right? So we can use our well-known logical equivalences to show that two expressions are equivalent. And we do that by transforming one expression into the other, or we can transform both of them into some sort of neutral form, which we'll talk about too. So these are the logical equivalences. And by all means, you should have a copy of this in front of you when you write the exam. And not just this, there's actually a larger one somewhere that I'll show you guys. Right, and so that, yeah, idempotence, negation, De Morgan's law. So De Morgan's and distributivity are probably some of the more complex ones, also absorption. The other ones are sort of more straightforward. Implication equivalence is pretty important. Contrapositive is pretty important. Biconditional equivalence, yeah. So those are the ones, maybe the more complicated ones you want to focus on, and the other ones are sort of straightforward or almost obvious. Implication, so P implies Q, we get this sort of truth table. So where the only time it's false is when P is true and Q is false. And if the antecedent is false, then, oops, what did I do here? Oh, I can't even fix that. So this should be true. I must have copied that table over or something. Anyway, so if the antecedent is false, then the consequent is always true on an implication. So there's only one row that's actually false, and that's this guy here. All right, and so there's lots of ways to translate implication into English. If then is one of the more popular ones. So if I manage my time, then I will get good grades. And there's also, I will get good grades if I manage my time. Right, so that's equivalent. It's just sort of the sentence is moved around. I manage my time only if I get good grades. Right, so that's a little bit different. Oops. All right, so that means if for this statement to be true, then if I managed my time, or I had to have gotten good grades. Otherwise, the statement would be false. Is there another one? There might have been one more. It's slipping my mind right now. Biconditional equivalence. So P, if and only if Q. So that's this two-way arrow here. That means that, you know, and we've seen that's equivalent to P implies Q and Q implies P. And that's typically how we express it if we're trying to prove it, is we use this form. So that's logically equivalent to this. Yeah. All right, so given an implication statement, P implies Q, then of course the inverse is the negation of both terms, but keeping the antecedent and the consequent. So P stays at the antecedent, but it's negated, and Q goes to the consequent. The converse is Q implies P, and the contrapositive is not Q implies not P. And that's logically equivalent to P implies Q. A logical expression can be a tautology. So in this case, P implies P or Q. So if we did implication equivalence, then this would be not P or Q, which means that, is that a tautology? Yeah, so one of not P or P must be true, which makes the whole thing true. So tautology means always true, regardless of what values we give to P and Q. Contradiction means always false. And this is an example of it. P if and only if Q and not P and Q. Yeah, I'm not going to break that down here. And then in contingency, depends on the values. Right, so it depends on the values of your proposition. So it can be true or it can be false, depending on what values we give to P and Q. Disjunctive normal form. So if we have, so this is called a conjunction when we use the and. So if we have conjunctions that are joined by disjunctions, which is the or, then that's disjunctive normal form. And full disjunctive normal form means that all propositions are in every conjunction. Right, so in this case, these two expressions, this one and this one up here, are equivalent, but this is just the full disjunctive normal form of this guy. And the nice thing about the full disjunctive normal form is it corresponds to rows on a truth table. So if you make a truth table, you can quickly get to the full disjunctive normal form just by looking at what the true values are. So here, this is a true value. That means we're going to take P and Q and R, which we do here. This one has a true value as well. So we're going to take P and Q and not R, because we want to turn that false into a true, right? So we want to have true and true and true in each of these expressions. So we take whatever, so we negate the ones that are false. And here we finally have this truth value, which is false and true. So we want not P in order to turn that first F false into a true, and Q and R. Right, and the rest are false. So this is the truth table that corresponds to this full disjunctive normal form that we have up here. Does conjunctive normal form give anything special like disjunctive normal form? It gives, so if you know the trick, it's an easy jump to go from conjunctive normal form to disjunctive normal form. So yes, it generally has, you can prove with conjunctive normal form a contingency as well. But I think in general, we prefer to use full disjunctive normal form just because it's more clear and you don't make mistakes. But so for instance, to go from this guy here to this guy, I take no, I think I'm assuming you I'm assuming you just wrote that wrong. I don't know of a conjunctive normal form. I know of a disjunctive normal form and a full disjunctive normal form. So I'm just assuming that conjunctive normal was a typo. Yeah. Yeah. So to go from this to here, I take each term and then I add. So for instance, let's move over here a bit. So if I take my this guy here, so P and Q, oops, P and Q, and I want to turn that into a full disjunctive normal form, well, then I go, that's equal to P and Q and R, or P and Q and not R, right? So that's, when we did it on the assignments and things, we took every single step. You introduce, some true value, and then you turned it into, R or not R, and then you distributed it over the term. But it's fairly simple once you know those steps to just go straight from this to here, and then you do the same thing to this guy, and then you find that, well, two of the disjunctions were, or two of their conjunctions were the same, right? So then you eliminate one of them. So that's why, so Q and R would be, that's P and Q and R, or not P and Q and R. And then we could see that this conjunction is in there twice. So then you can just eliminate it, and then you finally get to this this form here. Okay, questions about the full disjunctive normal form? So there are questions about full disjunctive normal form on the exam, so be aware of that. Right. So yeah, and so another way that you can, because the full disjunctive normal form corresponds to the truth table, you can use full disjunctive normal form to prove that two expressions are equivalent. So you convert them both into the full disjunctive normal form, and then you see that they're the same. So up to maybe these are in a different order, but since all the disjunctions are associative, then it doesn't matter. Not associative, commutative. Right. So full disjunctive normal form can be used to prove a contingency. So if I have three propositions and my full disjunctive normal form has three conjunctions, then I know that's a contingency because I have 3 truth values and 5 false values in my truth table. If I wound up with 8 conjunctions, then it would be a tautology. And if I wound up with simply false, it's of course tautology. It's of course a contradiction, right? So if all of those were false, if I try to go to full disjunctive normal form and I just ended up with a false, then that's a contradiction. Okay. Predicate logic. We can turn predicates into propositions by using quantifiers. So typically, if I say something like x is greater than 3, I don't know what the truth value is. But if I use quantifiers, then there is a truth value. Now they're not quite as precise as knowing, so if I gave x a value, then I could say whether that's true or false. So quantifiers are usually a little more abstract in terms of they don't really specify a precise value, but they do allow you to have a true or false value. So universal quantifier means for all x, yeah, and in this case I have some expression here, and then in this case I have there exists an x, and then I have some expression here. So which one corresponds to the, well, I mean, it should be pretty obvious. Which one corresponds to there exists? Actually, I think that's maybe too easy of a question. Right, so all monkeys live in forests, that's obviously the for all, and some monkeys live in forests, that's obviously there exists. And it's important, so these simple statements, I can't, they get very specific about which operator we use. right? So whether I use the, that's not going to go. All right. So whether I use the implication or the and logical and operator, that's an important distinction. Existential, yeah. That's an important distinction that it's easy to get wrong. So if I actually put the logical and operator here, that means you know, I'm talking about the universe of discourse of, say, all animals. So if I used and instead of implies there, what I'm saying is that all animals are monkeys and that live in forests, which is not true. That's too strong a statement. So, and if I use an implies down here, then I'm saying there exists an animal, and if that animal is a monkey, it lives in the forest. But it's not really saying that. But the problem is that that animal might not be a monkey, right? So there exists an animal. If that animal is a monkey, it lives in the forest. Well, that animal might be a fish. So that doesn't correspond to some monkeys live in forests. That one's maybe a little trickier to get a hold of, but yeah. And in a sense, for all and there exists are complementary. So if I say for all x, p of x, that's equal to there exists an x. That's not p of x, right? So what did I say here? Not all x is p of x. So there exists an x that's not p of x. So that's sort of if not all monkeys live in the forest, then there exists at least one monkey that does not live in the forest, for example. On the other hand, if I say there does not exist q of x, that's the same as saying for all x, not q of x, right? So if I say no monkeys, there is no monkey that lives in the ocean, then I can say for all monkeys, none of them live in the ocean. So those two statements are equivalent. All right. Questions about the quantifiers? Okay. An argument. It's a series of premises that imply a conclusion. I'm going to go over this. Yeah, we'll see. So a series of premises that imply a conclusion. So these are the premises. So if they're all true, then that implies that our conclusion is true. So an argument is valid if the conclusion is true when the premises are true. We're not saying a valid argument does not necessarily mean the premises are true, but it is sound if it is valid and all the premises are true. Deduction, using inference rules to take known true statements and reach some conclusion. Right? So that's when we went over proofs, this is the sort of thing. And a proof is a series of deductions and intermediate conclusions that imply the main conclusion. So there's a little bit of overlap here in terms of deduction, proof, and argument. So in a sense, they can all be the same thing, but of course a proof is a superset of a deduction, and deduction is a superset of an argument, etc. So these are the inference rules. So addition, if I know that P is true, then I can say, well, P or anything is true. Simplification, if I know both of these things are true, then I can declare either of them is true on its own, etc., etc. Modus ponens is straightforward. If I know P is true and I know P implies Q, then I know Q is true. And on the other hand, if I know P implies Q is true, but not Q is true, which means Q is false, then P must also be false. Right. So these are, again, you should have these in front of you when you write the exam. Any questions on any of these? Universal instantiation. So if I know something is true for all of X, then I can instantiate this for any member. I can say, well, you know, whether it's already been instantiated or not, I can say that it's true for any specific instance of whatever my universe of discourse is. Existential generalization is not quite as powerful. All right, existential instantiation. If I know there exists something, if I know that there exists an animal that lives in the forest, then I can say, well, I'm going to pick C, and C lives in a forest. I don't know anything else about it, but I know that something exists that lives in a forest, so let's work with that. Generalization. So if I have some specific instance for which P is true, then I could say there exists P of X. And if I have an arbitrary variable for which P is true, that means for all X, P of X. So arbitrary, it's a bit of a vague concept, I guess, but it just means that I don't know anything about this thing. But I know that it has this P quality, which means that sort of everything must have that P quality. If I'm saying, in general, I don't know anything about this. It's hard to describe. All right, types of proofs. So direct proof, P implies Q, so I assume P, and then I use inference rules to try and arrive at Q. Indirect, contradiction, so I'm just going to assume whatever I'm trying to prove is false. I'm trying to prove P, then assume not P. And that works in reverse too. If I'm trying to prove not P, then I assume P is true. Contrapositive just means that if I'm proving P implies Q, then I will instead prove not Q implies not P, because sometimes that's easier. And you've probably seen that on the assignments when you try to prove that, if you go from an even number to the square of an even number, it's easier to go that way than to go from a square backwards. Vacuous proof means basically false implies true. If I'm trying to prove that P implies Q, but I show that P is false, then it's always true. It's vacuous. Biconditional, we talked about that before. So P if and only if Q, if I prove that P implies Q, and I also prove that Q implies P, then that's a biconditional proof. And case analysis, if I have a set of premises where it's P1 or P2 or P3 implies a conclusion, then I have to show that each one of those implies a conclusion, because one of them might be true, but it could be any one of them. Or one of them has to be true, but it could be any one of them. All right. How will proof questions be asked? Yeah. Pretty light on proof questions, I'll be honest. But again, I don't want to say too many specific things. So yeah, you can't walk through a proof, of course, but you should understand them. If I ask something specific, like I asked for if this is a valid argument, you would have to, yeah, or what method would you use for this proof? Yeah, we could ask that. What lemmas would you use? I mean, yeah, that would be harder, and it's also what lemmas you use is almost you don't need to use lemmas. You use it to make your proof more readable. Yeah, so it's I probably wouldn't ask that one specifically, but the other ones are all fair game. Anything where it's an application of logic. I guess you've seen on your was it a tutorial or the quiz? I think it was a tutorial where I asked you which rules could you use to prove to take these true statements and reach this conclusion. And yeah, so that's fair game. Any other questions on proofs? All right. So sequences and sums, arithmetic sequence, so that's of the form, so A is the starting. 35 questions on the exam, and you have 2 hours. But they are they're meant to be challenging. They're meant to, it's open book, but of course, as I mentioned earlier, a good open book exam means you don't really have time to go researching a question. So you should know it beforehand. But you know, you can look up terms like the inference rules or whatever, or logical equivalences. That's fine to have at your fingertips, but trying to look up some deeper concept, you won't have time to do it, or that's the idea. Induction. Oh yeah, I can go over induction. Oh, I left that out of that. Yeah, I'll come back to that. Yeah, that's funny because I based this off of last year's notes and I forgot induction last year too. So yeah, this goes to show you. Yeah, I'll think of a simple proof by induction. Actually, there might be an example somewhere later on. So just hang tight for now. All right. So an arithmetic sequence is so A is the starting term and D is the common difference. So the sequence goes A and then A plus D, A plus 2D, A plus 3D. So each term in the sequence differs by some constant. A geometric sequence means each term in the sequence differs by a factor. So A again is the starting term, and then R is the common ratio. So A times R, and then AR squared, AR cubed, etc. So a series means that all terms in a sequence are operands in the addition. So if I took this geometric series, that means A plus AR plus AR squared plus AR cubed. That would be the series. And then the sum is, of course, when I add all those things up. Right, and we use sigma notation to represent a sum usually. And in general, it goes, so we have some counter variable, the I, A is the start value and B is the end value, and then we have some expression. That expression can include I or A or B or all of them, it doesn't matter. And it can also include other variables from other nested sums. Here's a few simple examples of sums. So I equals 1 to n of some constant, in this case 1. So then that means I'm just adding 1 to itself n times. So the answer is, of course, n. If that was a 2, then that would be 2n, etc. I equals 1 to n of n. Well, n is still a constant. N doesn't change, even though it's a variable. So it's just n plus itself n times, which means it's n times n, or n squared. Right. So in this case, this is 1 times n, and in this case, this is n times n. So they look different, but they're not. N is a constant, and so is 1. And of course, one of the most common sums that we use, if we count I equals 1 to n of I, so then the value is changing, so we add it up. So we add up all the numbers between 1 and n, and then we have this closed form, n times n plus 1 over 2. And you should definitely know that for the final. All right. So we're gonna, I'll get to, we can do the example on the practice quiz for this sigma notation. If you have any specific questions about it, I can answer them now. Or we can wait and do that question, and then I can introduce some more examples then if you want. All right. Okay. So set theory, a set is an unordered a set is an unordered collection where we don't count the duplicates. So in this case, 312, that's equal to, 1, 2, 3. It's also equal to 1, 1, 2, 3, etc. The cardinality of a set we represent like this. So set A has sort of this absolute value sign A elements. So that's the cardinality of A. And it is possible to have infinite sets. Oh yeah, and that's another thing we can go over at the end if you want is even though it's not part of the thing, I did figure out, somebody asked a question of why the power set on infinite sets is uncountable, or to explain it. And I did come up with a better explanation, but I'll save that for the end because it's not really part of the exam. We can use set builder notation to define sets. So we use predicates. So a set A could be X, all the values that are even. So this is the set of even numbers. And typically, you can often figure out the universe of discourse from the context. But if you were really going to be a stickler about it, we should, say for all X element of the integers, for instance. Actually, even if you use the real numbers, the even numbers are still part of the real numbers. So you would need some superset of the integers. And we can, so these are, these predicates use X is even, so it has a value of true or false for every given value that we want to look at. And so since these are propositions, we can use these logical operators. So we can say, I have a value X, and if it's odd and it's greater than 0, then it's part of my set. And that would be the set of positive odd numbers. A subset B, A is a subset of B, so that's the, and that is a proposition, so it has a value of true or false. A is a member of, or X is a member of A, so X is in the set A. So that's sort of the membership operator, and this other one here is the subset operator. Now these other set operators are a little bit different because they return sets. So these ones up here are propositions that return true or false. These ones return sets. So A union B is the set of all the values X such that X is in A or X is in B, right? So if I had two sets, then I just sort of combine all the elements of those two sets into one. A intersect B is all the elements that are in A and also in B. So they have to be in both A and B for them to be in that set. So, if I did had some two sets here and use this Venn diagram, then A intersect B is, of course, everything in here. And then A set difference B, well, that's all the elements that are in A and all the elements that are not in B. And that's one of the set equivalences that we're going to see as well. So that's the difference equivalence. So sets have membership tables that look an awful lot like our truth tables, except that we use zeros and ones to represent them. So a 1 means that some element is in set A and some element is in set E, so then it's definitely in the union. Here we say, well, we have an element that's in set A but not in set B, well, then it's also in the union. And here we say, well, it's in B but not in A, well, it's also in the union. And if it's in, if I have an element that's neither in set A or B, then it's not in the union. So that's how these membership tables work. And yeah, here's an example of a Venn diagram. Slow me down if I'm going too fast, or is yeah. So these set operations are we're okay with. I mean, they're almost a review. If you understand logic, it's very, very similar, although not quite exactly the same. Yeah, and this is Venn diagram. So if I have a set of even numbers and a set of prime numbers, then the intersection includes the numbers that are both even and prime, or is just that single value of 2. Yeah, and then if I took even set difference prime, then I would have all the even numbers except for 2, because 2 is also in the prime numbers. All right, so I can take the Cartesian product of 2 sets, and when I take Cartesian product, I end up using tuples. Oh, my pen is not working so good. So if I have a set A equals 1 and 2 and B equals 3 and 4, then I take the first element from A, and I take every element from B, so it's 1, 1, 1, 2. And these are tuples, so we use these round brackets, and the order matters in these. And you can have duplicates. So these are sequences or tuples, they're not sets. So once I've done that for 1, so I did that for 1, and then let's say for 2, then I take, oh, that's A, that's A times A. So this is 2, and I take the 2 maps to 1, and then 2 maps to 2. So that's A Cartesian product with itself. A Cartesian product with B is 1. I take 1 and I map it to 3 and 4. And then I take 2 and I map it to 3 and 4. All right, sorry about, yeah, I got a little confused. I did them out of order, but yeah, so it's Cartesian product, okay. All right. Set identities. I didn't put the sheet in here. I think it's the set identities. So these are very similar to logical equivalences, and we'll see them. So the set identities, all of the things that you should know are actually, I embedded it in the, when we take up the practice exam. So these are, so you'll see them there. Actually, I can switch to that right now. Yeah, so here we go is, these are both our set identities and logical equivalences. So yeah, the A intersect to the universe gives you A. A union, the empty set, gives you A as well. So those are identity. Domination, if I take A union the universe, I just get the universe. A intersect nothing, I get nothing, et cetera, et cetera. So De Morgan's, again, is something that's one of the more complicated ones that we use in distributivity. Oh, I got cut off there. So this should be, all right. All right, graph theory. So that is something that is definitely on the final. So graph is a tuple. So graph G is an ordered pair of vertices and edges, and the vertices are a set of entities. So, and the edges are a set of sets, pairs of vertices if it's a undirected graph, and it's a tuple if it is a directed graph. So if I added in edges here, or let's say I had this graph instead, then my edge set would be 1, 2, 2, 3, and 3, 1. And the order matters in this case. So a simple graph means no multi-edges or self-loops. So multi-edge means I have 2 edges, and a self-loop means I have an edge that links a vertex to itself. And so most of the graphs we deal with are simple graphs, unless we say otherwise. You can assume it's a simple graph. But directed or undirected, you should pay attention because we deal with both of those. Representation, adjacency list or an adjacency matrix. So an adjacency list of this graph would be, I would just put each vertex and then list all the things that it's incident on. So 2 is a neighbor of 1, and 2 is mapped to 3, and 3 is mapped to 1. So you can have this adjacency list for this directed graph. For an undirected graph, I would say 1, 2, 3, and then I would list 2 and 3, 1 and 3, and 2 and 1, or 1 and 2, or whatever. Adjacency matrix. So for this, again, let's say 1, 2, 3, 1, 2, 3. So I just make a table basically. And then I can put a 1 wherever I have an edge. So if I'm doing my directed graph, or let's do the, let's say this is the undirected one first. So 1 is a neighbor of 2 and 3. 2 is a neighbor of 1 and 3, and 3 is a neighbor of 1 and 2. And then I have zeros along there. So that's how we represent an adjacency matrix. And again, if I wanted to represent this directed graph as an adjacency matrix, I would simply only have them going one way. So 1 is a neighbor of 2, 2 is a neighbor of 3, and 3 is a neighbor of 1, and everything else we get a 0. Okay, questions about adjacency lists or adjacency matrices or? All right. So you should be aware of some popular graphs, in particular the complete graph, cycle graph, wheel graph. Definitely complete graph and the cycle graph. Bipartite graph means there's 2 distinct sets of vertices, and there's no edges between the 2 sets, right? So if I take this guy to be set V1 and this guy to set V2, so all my edges have 1 vertex in V1 and 1 vertex in V2. And a complete graph is, of course, that's a very important one. So a complete graph on, say, 4 vertices means everybody is connected to everybody else. So I would put as many edges as I can. So this is K4. Yes, bipartite only has 2 sets. That's true. Bipartite always has only 2 sets. There might be something called a tripartite graph or something like that. And if there isn't, you can definitely define one. But bipartite graphs occur a lot more often. And so they're a lot more common, and you'll definitely see them again. So a subgraph of G we could say is G prime. It doesn't have to be G prime. It's just, this is just a common notation of it. Equals V prime. E prime where V prime is a subset of V and E prime is a subset of E. Did I say that? I think I said that right. Right, so that's using the set notation because vertices and edges are both sets. So that's a subgraph. A spanning subgraph means G prime has all the vertices of G, but some subset of the edges. So that's a spanning subgraph means it includes all vertices. A spanning tree is a spanning subgraph with the least number of edges. Equivalently, it's a spanning subgraph that is a tree. That's the second definition is probably easier, but they're both they both mean the same thing. A search algorithm will produce a spanning subgraph of a connected component. Yeah, so some vertices are not searched. So if your graph is disconnected, then yeah, some vertices will be left out. And in fact, search algorithms are one way to figure out if your graph is disconnected or not. But when we say that it produces a spanning tree, yeah, sometimes they look connected, but they're directional, so they're not fully connected. Yes, that's a good point too. There can be sort of isolated vertices that are only outgoing vertices. Those are called, well, I mean, it depends on the context, but a lot of times they're called sources. And then if you have a vertex that has only incoming edges, those are called sinks. But that's a little bit further down the road of graph theory. So yeah, your spanning tree in a directed graph, even though if your graph is weakly connected, your spanning tree still might not include all the vertices. But if it's strongly connected, then it will. Right. So here is an example of a tree. It's a connected graph with no cycles. All right. So this is an example of a tree, and I could have I can add as many as many other sort of vertices and edges as I want, but as soon as I do this, then it's no longer a tree. Now it has a cycle. Another way to recognize this is it only has one face. So if I say a graph is connected, there's a path between every pair of vertices. This is for undirected graphs. A directed graph is strongly connected if for every pair of vertices A and B, there is a path from A to B and a path from B to A. And a directed graph is weakly connected if for every pair of vertices A and B, there's a path from A to B or a path from B to A. All right, so the difference between strongly connected and weakly connected is this and or basically in this definition. Yes. Good. Any questions about that? All right. Planar graph. So a planar graph can be drawn with no crossing edges. That's the definition. Planar representation is actually drawing it with no crossings. So as we talked about before, K4 has a planar representation, but you can draw it with crossing edges if you really wanted to. K4 is planar, but only one of these is the planar representation. Isomorphic graphs that are the same up to a relabeling of vertices. Right? So if I said 1, 2, 3, A, B, C, those two graphs are isomorphic, which means they're kind of the same. They have the same properties, basically. Graph coloring. So a valid coloring is assigning values, which are we call colors, to the vertices such that no two neighboring vertices have the same color. right? So that should be pretty straightforward. And a chromatic number is the least number of colors needed for a valid coloring. And we are going to see, when we take up the practice quiz, we'll see examples of chromatic number. So one of them I already did for the graphs that are there. And the other one we'll try and do live. Hopefully I don't make a mistake. And we'll talk a little bit about strategies and how you can sort of minimize your own mistakes on these things. Graph searching. So a depth first search is roughly this algorithm. So while there are unvisited vertices, we visit an unvisited neighbor. And then once we're at some vertex and I have no more unvisited neighbors, then I backtrack until the last vertex with an unvisited neighbor and return to 1. So that's sort of the quick and dirty version of that algorithm. And the breadth first search is a little more complicated. So we add the current vertex to a list, and we mark it as visited. And then we mark all the children of the vertex as visited. We add all the children of our current vertex to the back of the list. And then V gets the next vertex in the list, and we return back to 2. And again, we will see examples of how we would run through that when we get to the practice final. Both of them generate trees. If you take, when I'm at a vertex and I visit another vertex, then I add that edge, basically, and that's how I get my tree. So the depth first search tree tends to be a lot deeper. The breadth first search tree is actually the shortest path tree from the start vertex. All right. Depth first search, breadth first search, any questions? We will go through an example on the practice final. So. Models of computation. So we choose a representative operation. So that might be, memory access. That typically tends to be pretty expensive. And then we count that operation for a given problem size. And so what we select is sort of the model of computation. And we've seen examples of taking an algorithm written in either code or pseudocode and then counting certain operations. We counted foo and bar on the last assignment, which were just arbitrary operations. So you can your model of computation can be any type of any operation. Big O, big omega, big theta. So these functions, these are sets of functions, and they're classified according to the term that grows the fastest with regards to input, right? So these are, classifiers. Each one of these is a set of functions that all grow at the same rate, roughly speaking. And so the definition is big O f of x, a function f of x is big O of g of x. If there exists two constants c and k that are greater than 0, such that for all x greater than or equal to k, f of x is less than or equal to c times g of x. Yeah, and we'll do some examples on the quiz. Big omega is basically the same thing. We want the two constants, and we want all x greater than or equal to k, but in this case, instead of less than or equal to that we get up in big O, we get this greater than or equal to c times g of x. And big theta is simply if it's big O and big omega of the same function, then we say it's big theta of that function. So that means it's sort of a tight bound on the growth of that function. I did do some examples. Yeah, so there's basically 4 main types of big O and big omega questions. So the first one, so big O are the simpler ones. So if I have a function here, f of x equals 2x squared plus 3x plus 6, And if I want to show that it's big O of x squared, well, all of these are all positive coefficients. So I can simply say, well, I take each term and I bump it up to the highest polynomial, and then that's true for all x greater than or equal to 1. And then I just add all these terms up, which is 11x squared. And again, this is less than or equal to this as long as our x is greater than or equal to 1. So that means that our k is equal to 1, so that's the 1 that's over here, and our c is equal to 11, that's that guy there. Right, so that's the simplest version. Big O with negative coefficients is nearly as simple. So here we have 2x squared minus 3x plus 6. So we can say, well, we can get rid of that negative term and say that that's less than or equal to 2x squared plus 6, as long as x is greater than 0. That's true. And then we could say that's less than this if we bump this 6 up to the highest polynomial, which is x squared. But that's true now for all x greater than or equal to 1. And then we just add them together. And so we have our k equals 1 and our c equals 8. Okay. Any questions? Or is that? So big O should be hopefully pretty straightforward. If you have any questions, ask them now. All right, big omega, all positive coefficients. Again, that's sort of the simple version. So now we're using greater than or equal to instead of less than or equal to. So our f of x is 2x squared plus 3x plus 6. And since these are positive terms, we just drop them. So then it's greater than 2x squared for all x greater than or equal to 1. So then f of x is big omega of x squared with c equal to 2 and k equal to 1. Big omega with some negative coefficients. This is perhaps the most complicated one, although any one of them can trip you up if you're not careful. So f of x equals 2x squared minus 3x plus 6 is big omega of x squared. Well, now we want to, so the problem is that to start with, this function decreases, but we want to find a function that bounds it from below. So, and because x squared doesn't decrease, then we have to take, so we're going to take this 2x squared and we're going to divide it into x squared and x squared, right? So these two expressions are equal, but now I've grouped these terms together. So this whole line is true. And what I want is for this positive x squared to cancel out my negative 3x term, right? So then I want to look at, well, when does that happen? So this is greater than 0 for all x greater than or equal to 3. 3 works. A lot of other numbers work as well. I could take 4, 5, 6, 10. But when x is equal to 3, I get 9. It's 9 minus 9 plus 6 greater than 0, which is true. So then I could say, well, x squared plus this term is greater than or equal to x squared for all x greater than or equal to 3, right? Because when x is greater than or equal to 3, this becomes positive. So x squared plus something positive is greater than or equal to x squared. So now I have my two constants. There's an implicit 1 here. So f of x is big omega of x squared with c equal to 1 and k equal to 3. Okay. Questions on that? All right. Here's an important thing that you might see. So there are questions that are maybe a little more advanced that we put on there sometimes to differentiate between the people who are really getting the material and the people who are maybe not quite getting all of it. But so we can have a function like this: 5x cubed plus 3x squared sine x plus 2x cos x plus 7. And so spoiler alert, there are questions like that on the exam. Now, a lot of the exam is random, so you may not see this, but you might. So what we know about sine x and cos x, they're periodic functions that range between -1 and 1. So if you graph them, they both look like this. And they just do that forever. So they just oscillate between -1 and 1 as x goes from 0 to infinity. So that means when you're proving big O, you should assume they are equal to 1 because that is the maximum that they'll ever be. And if you're proving big omega, you should assume they're equal to -1. So you should sort of assume the one that is worse for you. So you should proving big O, you want to make your function as big as possible and then find something that's bigger. And if you're proving big omega, you want to make your function as small as possible and then find something that's smaller. Right? So that's how you handle this this sine and cos. This also helps differentiate between the students who come to the lectures and the students who watch the videos and the ones who don't. Right, so here, if I wanted to do big O of this function, I could just say, well, that's less than or equal to 5x squared plus 3x squared plus 2x plus 7. So I assume the sine x and the cos x are equal to 1, right? And then continue normally. From there, you know how to do it. And if I do big omega, then I would say, well, this is greater than or equal to 5x squared minus 3x squared minus 2x plus 7 for all x greater than or equal to 1, because that's sort of the smallest my function could be, and then continue normally. All right. Any questions on that? Okay, 6:52. Well, it's taking longer than I thought, but that's, as long as you guys are hanging in there, that's fine. I think we'll take a 10-minute break now, though, and I'll try and maybe go, well, I don't want to go too fast, but we'll take a 10-minute break. We'll come back at 7, that's not it, 7:04. Okay, so we're back. All right, so we're almost through with the review, and then we'll move on to the practice exam. So functions, we've already talked a little bit about functions. Functions are a mapping from a set A to a set B, and we write them like this. And they're mapping such that every element of A is mapped to exactly one element of B. And so that's the definition of a function. So A is known as the domain, B is known as the codomain, and for a function f that maps x to B, then x is the preimage and B is the image. If we take all of the B's, so everything that is mapped to from something in A, that's called the range of f. And so an injective function, which is a one-to-one function, so every image has how many pre-images? So it can be at least one or at most one. No, well, if it's surjective and it's injective, then they have one, exactly one. So injective means at most one. And surjective means at least one. And a bijective function means it's one-to-one and onto, and every image has exactly one. Right, so just a quick little A, B. So can this, can I make an injective function out of this? So each one of these has to map to something. And I have more things in my domain than I do in my codomain. So in this case, this is surjective, but not injective. Right, because I have less elements in my codomain. If I had the opposite problem, well then it can be one-to-one injective, but it can't be surjective. So I assume that we don't call it a function only if the preimage is connected to more than one image. Yes, right. That's well, that's a relation, right? But yeah, it's not a function if I have more than one arrow coming out from any of the preimages. Right, that's correct. All right, so and if, yeah. Right, also if a preimage, that's correct. If, yes, if a preimage doesn't have an image, so if I have, for instance, if my 3 here lost its mapping, then it that's not a function either. Yeah, good job. And for it to be bijective, if it's one-to-one and onto, what do I know about the cardinalities of the two sets? So cardinality being the number of elements. Yeah, so the cardinality has to be equal. And if we want surjective but not injective, then of course, codomain is smaller. And if we want injective but not surjective, then the domain has to be smaller than the codomain. Okay, so any other questions about functions? Okay, so relations. Relation is any subset of the Cartesian product of two sets, right? So if I have two sets, A and B, then the set of tuples 1 comma B and 1 comma C is a relation on A and B, which we labeled R1 here. R2 could be 1A, 2 to B, 3 to C. Again, now it's a relation is similar to a function, but it's less restrictive. It's actually a superset of the function. Well, super, yeah, it's not really, functions aren't really defined as sets, so I guess maybe they could be. R3 is 1 comma C, 2 map to C. Those are all valid relations. So a relation has a lot more flexibility than a function. And so a relation is a set, so we can also do set operations, right? So if we take the two R1 union R3, is that what I have here? Yeah. R1 union R3, well then I take each distinct element. So I have 1 comma B, 1 comma C. I have 1 comma C here again. Well, it's a set, so I don't repeat it. And I have 2 comma C. So yeah, this has R1 union R3 has these 3 elements. And we can do, of course, I didn't show them, but you could do R1 intersect R3, which gives you, I believe, 1C. Right, you can compose relations. So if I have a set A and a relation on A, R1 maps A to itself like this, and R2 maps A to itself like this, then R2 followed by R1, which is what this means. So if I drew that out, 1, 2, 3, 1, 2, 3, 1, 2, 3. So these are all A, but this is R1 and this is R2. So R1 is 1 to 1, 1 to 2, and 1 to 3. And R2 is 2 to 3 and 3 to 1. All right, so then I can just, when I compose them, I can either do it by, I say, well, I start with 1 to 1, and then I look, R2 does not map 1 to anything, so I can skip it. 1 to 2, and then R2 maps 2 to 3. So I have this term 1 and 3, and then R1 maps 1 to 3, and R2 maps 3 to 1, so I get a 1, 1 here. Right? So then, yeah, these are simply following as many valid paths as I can from the first set to the last set. And relations are reflexive if every element maps to itself, right? So for a reflexive relation on 1, 2, 3, it would have to include 1, 1, 2, 2, and 3, 3. And then it could have some other stuff. So that's reflexive. It's symmetric if xy being a member of that relation implies that yx is a member of that relation, right? So if I have a relation R and I have 1, 2, then I must also have 2, 1 in order for it to be symmetric, and then whatever else. So for every element that maps x to y, I also must have a relation that maps y to x. And R is anti-symmetric if the opposite is true. So if I have R equals 1, 2, then I cannot have 2, 1. The only thing that I'm allowed is I can have elements that map to themselves. So I can have 1, 1. So that's an anti-symmetric relation. And it's transitive if I have xy and yz, then I must also have xz. Right? So simple transitive relation would be 1, 2, and 2, 3. Then I must also have 1, 3. And that's a transitive relation. All right. And we can do closures on all those things. And what a closure means, well, that's again something we'll visit on the practice final. Have a regular OR operator in the transitive one. I have a logical and there. Oh, anti-symmetry. I'm not sure. Where's my logical OR? So I have an and. Okay, yeah, no problem. So what this means is that if I have X and Y, if I have a member XY as a member of the relation, so here I have 1, 2, and I have YX, then X must be equal to Y. And what that means is that if I have 1, 2, if I have 1, 2, I can't have 2, 1. But of course, that's what it means in general. But of course, there's one exception, and that's where, well, if I have one mapped to itself, then technically that makes this statement true, right? I have both of these things. I have, if X is equal to 1 and Y is equal to 1, then this can be true. I don't know if that makes sense. Yeah, yeah. The math sometimes, the formal math can throw you. I know it used to throw me, and it still does sometimes. You know, it is a more precise way of defining these things, but then sometimes it's tough to absorb it. All right, so an equivalence class is reflexive, symmetric, and transitive. And of course, if we have some set of relations in an equivalence class, then what it does is it divides it up into, sorry, it shouldn't be equivalence class, it should be equivalence relation. And it divides it into, these are the equivalence classes. So that means that you have classes where everything is related to everything, but there's no overlap between classes. So it sort of subdivides your set into, things that are equivalent. And a partial order is reflexive, antisymmetric, and transitive. That just means that, well, if we remember our Haas diagram, it means if you follow any path, there'll never be a cycle, basically. But you can, but it's not a tree because it's, well, a Haas diagram is technically a directed graph, right? So if I had this is a Haas diagram. And there's lots of edges here that are implied, but that don't exist. So this would actually look like, if I added in all the edges that weren't there, you would have these self loops. Yeah, let's just, if I did the simplest Haas diagram possible, then that's what it would look like. So it just means that there's some order. I always make progress, and I never revisit something if I'm following the relations. And then you can use it. It's sort of, it can represent the total order, and that's just it's a more general way of saying that I can put things in order. But the difference between a partial order is that sometimes I can't compare two things. They're in different streams or whatever. Countable sets. So a set A is countable if A is finite or there is a bijection between A and the positive integers. This is stuff we did last week. So, and as a couple examples, rational numbers are countable. So rational means P or over Q for integers P and Q. The real numbers are not countable. And the power set of positive integers is not countable. I don't think I'm going to get into that proof, but basically what you can show is that we can use the proof of that we did of the real numbers and show that there's a bijection between the power set and the real numbers. And it turns out that countable sets are the foundation of discrete math. Okay, and algorithms, this is not going to be on the final, but greedy algorithms, divide and conquer, and hill climbing. Hopefully you're slightly familiar with that stuff. All right, so any questions before we move on to the practice final? Definition questions. There's no definition questions per se, but we use definitions when we ask the questions, right? So you should understand them. Yeah, so a good question means that I'm testing multiple things, right? So you should understand the definitions, you should understand how to apply the concepts, and you should yeah, be able to work through them. And you should even, you know, once you get really good at it, you should be able to combine these concepts and stuff like that. So there's no straight up definition questions, but you will be asked the definitions as part of the question. So spanning tree, sure. Yeah, so a spanning tree. So there's you can find a general spanning tree, but also when you do your depth first search and breadth first search, you end up with spanning trees. So let me just, so just ignore this stuff. Whoops. Spanning tree. So a spanning tree just means, so if I have some graph, let's say like this, I'm going to select some subset of edges that spans all the vertices. That is also a tree, right? So I can take any old spanning tree just by selecting edges. So if I select that guy and this guy, as long as I don't make a cycle, I end up with a tree. And this guy. So that's a spanning tree, all those yellow things. So it's some subset of the edges of a graph. So we often think of spanning trees as subgraphs. Now, if we did a search on this, we would also get a spanning tree. So let's say, so let's do, we're going to start at this vertex and do a depth first search. So we go to our, so they're not labeled here, but if they were labeled, you would go to the smallest label. But let's just go here first, and then we go here, and then we can't go back to any one we've already visited. So then we go there, and then we go there. So that's a valid depth first search, and then that green path forms your depth first search tree. And if you did a breadth first search, well, if I started here, oops, yeah, that's ugly. Let me redraw this very simple graph. Nothing about weight, right? We'd you're thinking about minimum spanning tree, I guess. So when we do, yeah, so we don't do minimum spanning trees here in this class. You'll do them 3804. And yeah, then you would consider the weight. So you want the least weight. If you, any spanning tree here is a minimum spanning tree because every edge sort of implicitly has a weight of 1. So you can choose any tree, and that's the minimum spanning tree. Yeah, so if we did a breadth first search starting here, then we would go out simultaneously to all the neighbors, and then whichever one we chose next. So maybe we go to this guy next, but we don't have any unvisited neighbors, so we go here, and then we add this last edge. So that's the breadth first search tree. Okay, good. All right. Any other questions about spanning trees? We'll do, we could do another example on the practice quiz, if you want. Okay, so here, the practice quiz. So these are the logical, the logic expressions. logic questions. So is this a tautology, a contradiction, or a contingency? Oops. Justify your answer using only truth tables, and again, using only logical equivalences. So to do that with a truth table would be quite simple, right? So you do the truth table, and then the final column, which should have this expression. If it's all true values, then it's tautology. If it's all false values, it's contradiction. And if it's a mix, then it's a contingency, right? So how do we justify it? Using only logical equivalences. You remember how to do that? So that is the, we put it in full disjunctive normal form, right? And we do that because full disjunctive normal form is, so it sort of has a one-to-one correspondence to the truth table, right? So every true value in the last column of my truth table corresponds to a conjunction in my full disjunctive normal form. So if we put it in full disjunctive normal form, you can prove also that it's a tautology or a contradiction or a contingency. Oops. Are these two logically equivalent? How could we justify it? So last column of truth table. What if you just simplify it to true, then it's a tautology, yeah. So that is true, you could end up doing that. And that's, if you tried to put it in full disjunctive normal form, you would have, if you had, 3 terms, you could end up with, if you had 3 propositions, an expression on 3 propositions, then if you had 8 conjunctions, then it's also a tautology, because that's every row in your truth table. But yes, if you do bring it down to true, then that's also a tautology. Last column is the same. Or F full disjunctive normal form is the same. So those are the 2 ways you could do it. And the way you would prove that it was not is, of course, the last column is different, or the full disjunctive normal form has different conjunctions in it. What are the dimensions required for a truth table of this? Complete the truth table and use it to construct the full disjunctive normal form. So hopefully you were paying attention earlier when we showed you the one-to-one correspondence of the truth table to the full disjunctive normal form. This would have the number of rows is equal to the number of propositions raised to the power 2, or 2 raised to the power of the number of propositions. So this would have 8 rows, since it's 2 to the 3. Number of columns, that's a little harder, so we would have to count them, P, Q, R, and then we also have a not Q, and then we have not Q implies R, and then we have P or not Q implies R, and then we have not that, and then not that again. So we would have 2 more. So we would have 1, 2, 3, 4, 5, 6, 7, 8 columns. So the number of rows depends on the number of propositions, and the number of columns depends on the expression. Okay. Questions about any of that? All right. Here is the parts of it got cut off, I guess, but this quiz for week 4, this is quiz, oh, this is an old quiz. I think this is quiz 3 this appears on. So if you look back to quiz 3, it's there. And then set notation. So you're going to see a slightly different notation. So set difference, we're going to use this backslash, and complement is going to be raised to the C. So they mean essentially the same things as, set difference is A minus B, and if I did complement, that's equal to that. So which of these following sets is equivalent to the universe? I mean, you're going to use the same approach that you would actually second. Yeah, so you would try and use again your rules from up here and get it down to the U. And so it, in a lot of ways, it mirrors the logical equivalences and sort of the tautology and empty set. It's very, very similar. So you're using a lot of the same operations and the same sort of logic. Second one, you said the second one is the universe. Right, because it's union with the universe. Yep, good. The backslash is set difference, yeah. So yes, it's just this. The backslash is actually a pretty common terminology. It's used probably actually more than the minus sign. We sort of rolled with minus sign. I'm not sure why, but whatever. It's the logic is the same. You just both are used, but I've seen the backslash more than I've seen the minus. And the complement. I think maybe that might have been just for clarity, because once you start adding a lot of, so Robert made this question and he chose to this notation. And I believe it was for clarity, because once you start putting a lot of lines here, it gets kind of, I mean, you almost end up with a grid sometimes. So the C is just a little more clear. What type of sequence is 102, 569, 136, 1503? So yeah, you can find, I mean, it's quite easy, right? I take 569 minus 102, and that should equal 1036 minus 569. And I should do that for, each of these should have a common difference. If not, then it's not an arithmetic sequence. Or on the other hand, I could say, I could say 569 divided by 102. If it's geometric, then this should give me my common ratio. And then I should be able to, that should also be equal to 1036 divided by 569 equals R. And this means it's geometric, if that's true. And if not, it's not geometric. And this means arithmetic. And so, yeah, those are pretty straightforward. I don't think you should have too much trouble with those. And there's really not very many ways to trick you, except maybe, have them all. I guess we could be tricky, but I don't think there's any tricky questions there. They're all pretty straightforward. What expression using sigma notation represents the sum of integers from 37 to 211 inclusive? What is the closed form of this expression? Well, so we would have I equals 37 to 211 of I, right? So that's the sigma notation. And then to get the closed form, there's a couple ways I can get it. But one way, I guess the easiest way, is to use the difference of sums here. I equals 1, 211 of I minus I equals 1 up to 36. Right, and then I know how to do these guys. So it's 211 times 212 over 2 minus 36 times 37 over 2, right? I'm using the this closed form here, which is the most common. And you can do almost everything just by knowing this. And anything else you can look up. All right, so this would be the closed form of that. The other closed form is, I'm not sure if I remember it off the top of my head, so I'm not going to try it because I don't want to mislead you. But there is one for, I could take this directly into a closed form. So any questions about that? And you can get more complicated versions of it, but so I can say, you know, the sum from 37 to 211, except for everything divided by 4, well, then I would just, I could subtract minus, well, it's not, so that would be 40. So I, or J equals 10 to 211 divided by 4 is 52, I guess. Something like that. This might be this might be wrong. I did it quickly in my head, but and then you can break that down the same way you broke the other one. Nested sums being on the exam. You should, yeah. Do you want to see a nested sum? Yeah. All right, so if we did a nested sum and provided you a value, then it should be quite straightforward. So I could say I equals, let's do something simple here. I equals 1 to 100, and then j equals 1 to I of j. So the first thing I do is I can evaluate this using I as a constant. So I equals 1 to 100. And then I know how to do this. It's simply I plus 1 over 2. And now I got to break that down into I equals 1 over 1 to 100 of I squared over 2 plus I over 2. All right, and then this guy we know, so we can take out the common factor of, let's just do, actually take out the half, and we get I squared here plus 1/2 we know how to do this one, and this guy we can look up over here. So yeah, it's this term, this one here. All right, and so then we can, our n in this case is 100. Where did it go? Yeah, our n in this case is 100, so you can just substitute those in and solve it. Okay, I mean, I know I went over that pretty quickly, but is that sort of understandable? It's probably as complicated as you'll get with this type of question. Is there anything that's, yeah, okay, good. All right. Consider these adjacency matrices and answer the questions below for each graph being represented. Yeah, these are nasty. So just so you're all aware, these are combinatorial graphs. So these are generated randomly, which means that when I made your quizzes, you know, I had your nice, what did I do? I did some layout like this. And then I actually drew the graph first and then converted it to a matrix so that I knew it would be easy enough to draw. That's not going to work here. So these are, because they're randomly generated, you could have crossings. It's not necessarily going to be pretty. So when you draw it, I would recommend, so this is an example. You have 10 vertices, and I'd recommend drawing them in a circle because if you look at this mess of edges, I mean, that's all it is. It's a mess. So it's not going to, these aren't going to be pretty graphs, but you can still do all your computations on them. Okay, so in this case, what is the chromatic number? It's 3. And how do I know? Well, I colored all the vertices. I made sure that nobody was adjacent to somebody of the same color. And then I found some, you know, a K3. So chromatic number of 3. And I could take, there's a whole bunch of K3s in there that I could take. In particular, this, and this is K3. Yes, they're randomly generated. So yeah, they're going to be like messy like this. So this is sort of my recommended way to draw them. That way you're not really, if you try to draw it like using some sensible, you know, like I said before, you're just going to end up with a mess of like loops and stuff going, you know, way across your graph, and it's going to be messy. So probably this way is in a circle is the way to draw it that is the most clear. I would not try to do this. But they're randomly generated to have a certain complexity, right? So it's they're all going to be equally hard, so to speak. And the stuff you see on the practice exam is going to be the hardest, harder than anything you would see on the final. So this mess here, I don't think you'd see anything that dense, although I haven't looked at every single question. But yeah, so that's chromatic. Any questions on how to get the chromatic number? I'll show you how to do, so you can also do a breadth first search and depth first search starting at a random vertex. You can do it on your drawn graph here, or you can actually do it on the, you can just do it on the matrix itself, right? Let's see if I can, well, let's do it for the other one. So this one's not really all messed up like that. So if I wanted to do, say, a depth first search, or a breadth first search. So depth first search, let's start at, say, well, let's start at 0. So I'm just going to make a list of the vertices as I see them. So I'm starting here, and now I can look down the 0 row and to the first. So I want to take the vertex that I haven't visited yet, that is the smallest. And in this case, that's 2. So my next vertex I visit is 2. Now, because I'm visiting 2, I can go down to this row of the matrix, and 0, we've already visited, so I'm not going to write 0 down again. And the next one we see is 8. So we're going to write the 8 down, and then we'll go to the 8th row. 8 is neighbors with 1 and 2, but the first one we see is 1, and so then we go to the first row. So you can do it this way. I don't know that it's any easier. I think the breadth first search is easier to do that way. So if I did, and then so you'd keep going until you're going to write down a number that you've already written down before, and then you backtrack. So maybe that's more clear, maybe not. I don't know. But that is one valid way to do it. And if I did the breadth first search, starting at 0, and then I write down all my neighbors, right? So I'd write down 2, 4, and 6. So everywhere that I see a 1 in that first row. And now I go to my next number in the list. So 2, which means I go to row 2 and I write down 0, but I already have a 0, so I'd write down 8 at the end of the list. And then I go to the next number in the list, which is 4. 4 is 0, which we've already seen, and 8 and 9. Of those, only 9 we haven't seen. So then we go to 6. 6 has 0 and 1. We haven't seen 1 yet, so we're going to write that down. We have 3, which we haven't seen yet, so we'll write that down. And we have 8, which we've already seen, so we don't write that down. And then we go to the 8. So that's how you would do a breadth-first search until you've seen all the vertices. So I think breadth-first search on a matrix is actually quite easy. But again, if this feels confusing, then just, you know, draw your graph out and then do your search and make sure you mark the vertices that you've already been to and mark, you know, which edges you take, because you might be asked something about the spanning tree that's been generated. Okay. Is there any cut vertices on this graph? I mean, there isn't. It's too dense. There's nothing you can take away that's going to eliminate or split up your graph into 2 connected components. This guy, maybe, this guy's a little less dense, so there might be a cut vertex. Typically, anything that asks you for a cut vertex is not going to be that dense because once you add too many edges, then it becomes too connected, which means that you need to remove 2 vertices in order to disconnect your graph, or even worse than that. What else? How would you represent the resulting trees as an adjacency matrix or an adjacency list? Well, the adjacency matrix is, of course, this, but with less, you know, you would have less ones. And the adjacency list would be, of course, you would just list out your 0, 1, 2, up to 9, and then write down all the neighbors. You can pull that right from, that's pretty easy to pull right from the matrix itself, right? So for 0, I'd have 3, 5, 7. So I just write 3, 5, 7, and so on. So it's pretty easy to go back and forth from the adjacency matrix to the adjacency list. Cut edges. So can I remove an edge that disconnects this graph? In this case, no. The other one, maybe, if I wanted to draw it out. Chromatic number, and can we prove it? Yeah. So with that, yeah, that covers all the stuff on the trees. Is there any questions or anything you want me to go over again for these graph questions? When you ask to write the vertices in the search tree in the order they were visited, can you show us how to write that down? Yeah, sure. So, I mean, I started to do it here. So the depth first search, this is the order. And then, of course, I'm trying to do it from the matrix, but it's still the same order. And this one, what do I have here? I have, this is the order here as well. So if I continued it, so I'm at 8. 1, 2 are already there. 4, come on. 4 and 6 are already in the graph, so 8 adds nothing. So I go to 9. 1, 4. Which one is 0, 1, 2, 3, 4, 5? Anybody? Oh, I somehow missed 5. Oh yeah, when I get to 3, then I'd visit 5. So this would be the order that I would write it down for the breadth first search. Yep, 5's at the end. So when I finally get to 3, 3 is actually the only guy that's connected to 5. Yeah, and this, yeah, the same for the depth first search. So I didn't complete it here, but yeah. just the same order that you visit them. All right, any other questions on these graph theory questions? All right, consider the following functions. What functions g of x would each of these functions be big O, big omega, big theta? Right, so, I mean, as a general rule, it's going to be big O of the highest polynomial, or the highest, the most dominant term. So this is definitely big O of x to the 5th. It's also big O of x to the 6th. It's also big O of, I could keep going. And in terms of big omega, well, it is big omega of x to the 5th. I could find that out fairly quickly using limits. And then I could take some fraction of a half. Or I might, or another type of question you'll see is, so this is also, and I mean, it's also big omega of x to the 4th or anything below that. What values of c and k can I use to justify my answer? So I say this is, sorry, trying to find the button on my pen. So how can I justify that it's big O of x to the 5th? What values of c and k could I use? Well, I can just, since these are all positive, I can just say x to the 5th plus 17x to the 5th plus 5x to the 5th plus, plus x to the 5th, which is equal to 24x to the 5th. So I can use c equal to 24 and k equal to 1. So this is less than or equal to that for all x greater than or equal to 1. So we did run through some examples of how to do that. But what I might ask is similar to what you saw on your last quiz. I say, does it work with, if I take c equal to 5 and k equal to 10, are those valid witnesses? You might see a question like that. And then how I would, for this type of question, I would say, well, x to the 5th plus 17x cubed plus 5x squared plus x is less than or equal to, my c is 5, so 5x to the 5. And then I would substitute, for my x values, I would put the I would put the value 10 and see if this still holds true. And if it does, then those are valid witnesses. And if it doesn't, then they're not. All right. And similar for big omega, except in that case, I would say, well, is it greater than? And yeah. So does this work for big omega? Is c equal to 5 work for big omega? Is that, do you guys remember how the, yeah. And how I know is because the first term, the coefficient is less than 5. So it can't be 5 for big omega. Okay. And for big O, it's if my constant is greater than if my constant is less than the coefficient of the largest term, then that will never work. That will never work either. For one like this, remember that log x is big O of x. So I could say x cubed log x is less than or equal to x to the fourth for all x greater than or equal to 1. Okay. And remember what we talked about for the sine and cosine. Any other questions for big O? All right. Functions. So this function, is it injective, surjective, bijective? What is it? Let's say, is it injective first of all? No. Yeah, it's not injective, right? Because we have M maps to 3 and G maps to 3. So it's not one-to-one. Is it surjective? Yeah, it is surjective because every member of the codomain is part of the range. So every member gets maps to. Bijective, well, it has to be injective and surjective, so it's not bijective. So how would we change it to make it injective? Let's say we wanted to add elements, where would we add them? Or where would we take them away? Yeah, we would add more elements to the codomain. So if we wanted to define an injective function, we would need more elements in the codomain because there's more elements in the domain, so some of them have to double up on some image. And if I wanted to make it bijective, of course, they would have to have equal number of elements in the domain in the codomain. Right, so those should be, if you understand injective, surjective, and bijective, all of this should be straightforward. And again, this is a very open-ended question, and of course, on the final, since it's multiple choice, they are not open-ended. They'll be very, very specific. So the open-ended questions are just to help you think. Consider the following binary relation on the set. Is this relation reflexive? Is it reflexive? So do we remember what reflexive means? No. So for it to be reflexive, each element would have to map to itself, and we're missing quite a few. So we don't have 1-to-1, we don't have 2-to-2, we don't have 3-to-3, and we don't have 5-to-5. So how would we make it reflexive? We would just add all those elements. So the reflexive closure, we would add 1, 1, 2, 2, 3, 3, 4, 4 is already there, and 6, 6 is already there. So we would add these elements to get the reflexive closure. Is it symmetric? I'm not sure actually. 0, 1, do we have 1, 0? No. Right, so it's not symmetric. But again, the symmetric closure is fairly easy as well. So we would just add in, so we need 1, 0. We need 3, 0, etc. Right? So every time we see, if I see 0, 1, but there's no 1, 0, then I would have to add it in. But again, reflexive and symmetric closures are both one step. So we only need to do one step to get the full closure, to add enough elements to give it that property. Transitive closure is something a little bit different though. Right? So offhand, we could have to do it more than once. So is it transitive though? Maybe it is transitive. No. And I can see right away if I go 0, if I go 0, 1, and then I go 1, 2, so I need to have 0, 2, and I don't. Right. And, another example is there's 1, 4, and there's 4, 0, but no 4, 1. No 1, yeah, no 1, 0. Yes. So transitive closure, so to do the transitive closure, I basically look for elements. So I look for 0, 1. These would be separate. Yeah, that's actually, so that would be specified in the question, but most likely, so on the exam, again, because it's multiple choice, it would probably only be one at a time, right? Not on top of each other. So you'd be given a relation, and then maybe you'd be given a bunch of different sets, and which one is your reflexive closure, for instance? Questions like that. It won't be on top of each other. But yeah, that is a very good question because it does make a difference, or it can make a difference. Does it make a difference? Probably. So transitive closure, the difference between transitive closure, so for instance, I would say I would take my 0, 1 and 1, 2, and I would add, my first step of my transitive closure would include 0, 2. And then I'd have to go through and, 0, 3, 3, 1, do I have, well, I have 0, 1, that's fine. And so I would pick all those, but then once I add those, elements, then I might have to do it again on the, so actually to come back to your question, the transitive closure has to be applied on top of itself, right? Until you're not adding any more new elements. So I would take all of these and I would add it to this set, and then I would do the transitive closure again. And I would keep on doing it until I'm not adding any new elements. And then all of those elements are part of my transitive closure. Now again, this is very difficult. This would be a difficult question for the transitive closure, for sure. And it's very unlikely you see anything this complicated. In fact, I'm almost certain you don't, although as many times as I've been through the final exam, I haven't seen anything that complex, but do know how to do a transitive closure. So you might be asked for something like that on a much smaller relation. Number of times you add the elements, yeah, as many elements as you have in the set, right? So to be sure, you need to do it. So if, let's call this set R, this relation R, then you would need to do it a cardinality of R times, right? It's unlikely that you would need that many, but that is the upper bound. If you did it this many times, you would be sure to have the transitive closure. But that's not, it's not always practical either, unless the set's a lot smaller. All right. Any other questions? All right, and that's it, I guess. Okay. Was there something else I was going to show you? I don't remember now. Does anybody have anything they want to review again? Induction. Yeah. Sure. Let's say. Well, let's go with a classic. So let's say we want to show that sum of I equals 1 to n of I is equal to this. We'll show it by induction. All right, so what's the first step? What do we do first in induction? So this is, let's say this is our proposition P of n, right? Is that this is true. So the first step is the basis case. So we want to take the smallest possible value. So let's say 1, right? So if n is equal to 1, so P of 1. And what that is I equals 1 to 1 of I equals, now n is equal to 1, so 1, 1 plus 1 over 2, which is equal to 1, which is true. So if I sum up all the numbers from 1 to 1, it's equal to 1. So the basis case is true. So now I want to show the inductive step. So the inductive step is an implication. I want to show that P of k implies P of k plus 1. All right, so what that means is that, so let's start with P of k is our assumption. And what that means is that if I sum up I equals 1 to k, that is equal to k times k plus 1 over 2. That's the definition. P of k. 3. Now I want to try and make that into, I want to show that P of k implies P of k plus 1. So I want to try and get this and turn it into this, right? Because this is the definition of P of k plus 1. So how I'm going to do that is I'm just going to add, well, the left-hand side is fairly easy. If I add, sorry, there should be an I here. And should be an I here, plus k plus 1. And then I have to add k plus 1 to both sides. All right, so this is what I add to this to get this. Right, so now I know my left-hand side looks proper, looks correct. So now I have to see if I can turn this into this. So that's equal to k plus 1 over 2, and I want to get the common denominator. And that's equal to oof, what did I do here? So k squared plus k plus 2k plus 2. Is that right? Over 2. Ah, you know what? I'm making it too complicated. So I have 2 of k plus 1, and I have here, and I have k of k plus 1 here, so I have k plus 2, k plus 1 over 2, which is what I'm supposed to get. So, and this is P of k plus 1 by definition, and all of this is simply math. And that's it. So it's a lot of times we ask induction questions. Yes, so right. So the question is, how do I get from here plus k plus 1 to the other summation? Well, this is really just, if I look at this, is there a parentheses for number 3? Oh yeah, for sure. Sorry. Well, no, because I don't have to. If this was included in my summation, then it would be like this, but it's not. Right. So let's just expand it out. So this is I. What happened there? I equals 1 to k of I is equal to 1 plus 2 plus 3 up to k. And then I'm going to add k plus 1 to that. Right? So if I say I equals 1 to k plus 1, that's equal to 1 plus 2 plus 3 plus k plus 1. So if I add k plus 1 up here, then I get this. Right? So hopefully that's how I got from here to here. Yeah, okay. Good. Any other questions? All right. Well, I will be here to answer questions for the next 10 minutes. If you think of anything, other than that, I don't think there's office hours next week. I'd have to check, but I will be checking in on Discord. And you can direct message me on Discord as well, and I'll answer your questions if you have any. Yeah. All right, so that's it for tonight, guys. And yeah, it was great to, I mean, I wish I could have met you guys, but whatever. It is what it is right now.